So here's something worth sitting with for a moment. Right now, as you're lying there, settling in, maybe pulling the covers up a little, every single atom in your body, every bit of carbon in your muscles, every molecule of oxygen drifting through your lungs, the calcium in your bones, the iron in your blood, all of it was made inside a star that died before our sun was even born. You are, quite literally, ancient stardust that learned how to think. And if you trace that stardust back far enough, past the stars that forged it, past the clouds of gas that collapsed to form those stars, past the first galaxies, past the first light that ever shone in the cosmos, you arrive at a single moment. One moment, roughly 13.8 billion years ago, when everything, all of space, all of energy, all of time itself, emerged from something so unimaginably small and hot and dense that the human mind genuinely cannot picture it. Not because we're not smart enough, but because the rules of the universe we use to picture things hadn't been invented yet. They were part of what emerged. That's where we're going tonight. The whole story. From literally nothing, or as close to nothing as physics allows us to talk about, all the way to the universe you're floating through right now. And we're going to take it slow, because honestly, this story deserves to be taken slow. There's no rush. The universe took 13.8 billion years to get here. We can take our time. Let's start with the question itself, because the question is older than the science. Every civilization that's ever existed has looked up at the night sky and asked some version of it. Where did all of this come from? The Babylonians had their creation epics. The ancient Egyptians imagined the world rising out of a primordial ocean called Nun. Hindu cosmology describes cycles of creation and destruction stretching across incomprehensible spans of time. And honestly, that cyclical idea isn't so far from some things modern physicists have proposed, which we'll get to later. The ancient Greeks debated whether the cosmos was eternal or had a beginning. Aristotle argued for an eternal universe, one that had always existed and always would. And that idea, that the universe simply is with no starting point, was so elegant and so philosophically tidy that it dominated Western thinking for nearly 2,000 years. Think about that. For most of recorded human history, the smartest people in the room assumed the universe had no beginning. It was just there. Always had been. And if you'd suggested otherwise in, say, 1910, most physicists would have politely told you that you were being unscientific. The idea of a cosmic beginning sounded too much like religion, too much like mythology. Serious scientists dealt with eternal laws and steady states. A beginning implied a beginner, and that made people uncomfortable. But then something changed, and the person who changed it wasn't who you'd expect. In 1927, a Belgian Catholic priest named Georges Lemaître published a paper that would eventually reshape our entire understanding of existence. Now Lemaître wasn't just a priest. He was a brilliant physicist and mathematician who had studied at Cambridge under Arthur Eddington, one of the most respected astrophysicists of the era, and had earned a PhD from MIT. The man had serious credentials, and what he proposed was radical. He took Einstein's equations of general relativity, the ones Einstein himself had published about a decade earlier, and he showed that they naturally predicted something startling. The universe should be expanding, not sitting still, not eternal and unchanging. Expanding. Everything moving away from everything else, like dots painted on the surface of a balloon that's being inflated. Here's the thing about Einstein's equations. When Einstein first worked them out in 1915, he noticed the same implication. His own math was telling him the universe couldn't be static. It had to be either expanding or contracting. And Einstein didn't like that. It bothered him. It felt wrong. So he did something he'd later call the biggest blunder of his career. He added a fudge factor, a term called the cosmological constant, represented by the Greek letter lambda, which he stuck into his equations purely to force them to describe a static, eternal universe. He essentially put his thumb on the scale, because the answer his own math was giving him was too strange to accept. And then along comes Lemaître, this quiet, unassuming priest with round spectacles and a gentle demeanor, and he says, no, the equations are right as they are. The universe is expanding, and if it's expanding now, that means it was smaller yesterday, and smaller the day before that. And if you rewind the clock far enough, everything in the universe, all the matter, all the energy, all of space, was compressed into what he called the primeval atom, one unimaginably dense point from which everything burst forth. Now, the reaction to this idea was, let's say, mixed. Eddington, Lemaître's own mentor, found the concept repulsive. He said it was philosophically distasteful. Einstein, when he first heard Lemaître present the idea at a conference, reportedly told him, "Your calculations are correct, but your physics is abominable." Which is a fascinating thing to say, right? Your math is right, but I don't like your conclusion. That tells you a lot about how hard it is, even for geniuses, to accept something that breaks their worldview. But Lemaître had something more than elegant math. He had a prediction. If the universe is expanding, then distant galaxies should be moving away from us, and the farther away they are, the faster they should be receding. That's a testable prediction. And right around the same time, an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, with its enormous 100-inch telescope, the largest in the world at the time, was making observations that would confirm exactly that. Hubble wasn't specifically trying to prove Lemaître right. He was doing something more basic, measuring distances to galaxies and figuring out how fast they were moving. And the way he measured their motion is actually beautiful in its simplicity. You know how when an ambulance drives toward you, the siren sounds higher pitched, and when it drives away, it sounds lower? That's the Doppler effect. Light does the same thing. When a galaxy is moving away from us, its light gets stretched out, shifted toward the red end of the spectrum. The faster it's moving away, the more its light is redshifted. So by measuring the redshift of light from distant galaxies, Hubble could figure out how fast they were receding. And what he found, published in 1929, was remarkable. Every distant galaxy he looked at was moving away from us, and the farther away a galaxy was, the faster it was moving. This relationship, velocity proportional to distance, is now called Hubble's law, though in fairness, Lemaître had derived it theoretically 2 years before Hubble observed it. There's actually been a push in recent years to call it the Hubble-Lemaître law, which the International Astronomical Union formally adopted in 2018, a small act of historical justice, nearly a century late. So now you have this extraordinary convergence. Einstein's math predicts an expanding universe. Lemaître interprets that math and proposes the universe began from a single primordial point. Hubble observes galaxies flying apart in exactly the pattern you'd expect if the universe were expanding. The evidence is piling up. But the idea still had fierce opponents, and the fiercest of them would accidentally give it its most famous name. Fred Hoyle was a brilliant British astronomer, genuinely one of the great scientific minds of the 20th century. He made enormous contributions to our understanding of how elements are forged inside stars, work that arguably deserved a Nobel Prize, though he never received one, which is its own interesting story. But Hoyle was deeply opposed to the idea that the universe had a beginning. He championed an alternative called the steady-state theory, which proposed that the universe is eternal, has always been expanding, and that new matter is continuously created to fill in the gaps as galaxies drift apart. It's a clever idea, actually. It preserves the expanding universe that Hubble observed, but avoids the uncomfortable question of a beginning. And in 1949, during a BBC radio broadcast, Hoyle was describing the competing theories, and he referred to Lemaître's idea dismissively as this Big Bang idea. He probably didn't mean it as a formal name. It was more of a sneer. But it stuck. The Big Bang. That's what everyone started calling it. And here's the irony. The name is actually kind of misleading. When you hear Big Bang, you picture an explosion, right? Something blowing up in space, debris flying outward into the void. But that's not what happened. There was no pre-existing space for anything to explode into. Space itself was what was expanding. The Big Bang wasn't an explosion in space. It was an expansion of space. Everything wasn't flying apart from some central point. Every point was moving away from every other point, because the fabric of space between them was stretching. Think of it this way. Imagine you're a tiny ant standing on the surface of a balloon, and someone is blowing up the balloon. From your perspective, every other ant on the balloon is moving away from you. And the farther away they are, the faster they seem to recede. But no ant is at the center. There is no center on the surface of the balloon. Every point on the surface is equivalent. That's closer to what's actually happening with the expansion of the universe. There's no center. There's no edge. There's just more space, everywhere, all the time. Now, this is one of those ideas that's genuinely hard to wrap your head around, and that's okay. It's supposed to be hard. You're trying to use a brain that evolved to track predators on the African savanna, to comprehend the origin of space-time. Give yourself some grace. The key insight is just this. The universe isn't expanding into anything. It's not filling up some pre-existing empty room. The expansion is the creation of new space between things. And if you run that expansion backward, everything gets closer together, denser, hotter, until you reach a point where our current understanding of physics simply breaks down. That point, the very first instant, time zero, the moment of the Big Bang itself, is what physicists call a singularity. And a singularity is basically physics raising its hands and saying, I don't know. The math gives infinities, infinite density, infinite temperature, infinitely small volume. And whenever your equations spit out infinity, that's usually a sign that your theory is incomplete, that something deeper is going on that you don't have the tools to describe yet. It's like dividing by zero on a calculator. You don't get a meaningful answer. You get an error message. The singularity is the universe's error message. So here's an honest thing to say right up front. We don't actually know what happened at the very instant of the Big Bang, or what, if anything, came before it. We have ideas. Some of them are beautiful and mathematically sophisticated. But we don't have confirmed, tested, settled science for that first sliver of a second. What we do have, and this is what makes this story so extraordinary, is an incredibly detailed, well-tested understanding of what happened starting from a tiny fraction of a second after the Big Bang. we can describe the universe's evolution from roughly 1/1,000,000th of a second after the beginning all the way to the present day with remarkable precision. That's not a guess. That's backed by multiple independent lines of evidence that all point to the same story. And that story begins in conditions so extreme that they make the center of the sun look like a cool autumn afternoon. We're talking about temperatures in the trillions of degrees, energies so high that the fundamental forces of nature, the ones that today feel so different from each other, gravity and electromagnetism and the strong and weak nuclear forces, were likely unified, merged together into something we don't fully understand yet. A single superforce, maybe. The universe at that instant wasn't made of atoms, or even of the protons and neutrons that make up atoms. It was a seething, roiling soup of the most elementary particles and energy, everything smashing into everything else at nearly the speed of light, and the rules governing all of it were being written in real time as the universe cooled and expanded. And the cooling happened fast, unbelievably fast, because as space expanded, the energy spread out, and the temperature dropped, and as the temperature dropped, things started to happen. Symmetries broke, forces separated, particles that couldn't exist a moment earlier suddenly could. It's like watching water freeze. At high temperature, everything is fluid and uniform, but as it cools, structure appears, crystals form, patterns emerge. The universe was crystallizing into the laws of physics we know today. And the first of those phase transitions, the first great symmetry-breaking event, may have triggered something extraordinary, something so dramatic, so violently creative, that it may have shaped every large-scale structure you see in the night sky today. It's called cosmic inflation, and it's one of the most mind-bending ideas in all of physics. So picture this. The universe is less than 1/1,000,000th of a 1,000,000th of a 1,000,000th of a second old. That's 10 to the minus 36 seconds, give or take. It's unimaginably tiny, smaller than a proton, smaller than anything you could ever hope to see even with the most powerful instruments ever built. And something happens. Some field, permeating all of space, settles into a particular energy state, a kind of false vacuum, physicists call it, and the effect is like anti-gravity on steroids. Space doesn't just expand, it explodes outward exponentially. Not at the speed of light, not at 10 times the speed of light, but doubling in size over and over and over again in the tiniest sliver of time. In roughly 10 to the minus 32 seconds, we're still talking about a duration so short that no clock could ever measure it. The universe went from something smaller than an atom to something potentially larger than the observable universe is today. Let that sit for a moment. A region smaller than a subatomic particle, inflated to cosmic scales, in less time than it takes light to cross a single proton. Now, you might be thinking, wait, doesn't relativity say nothing can travel faster than light? And you're right, nothing can move through space faster than light, but space itself can expand as fast as it wants. There's no speed limit on the stretching of the fabric of the universe itself. That's a subtle but crucial distinction, and it's one that trips people up all the time. During inflation, no particle outran a photon. Instead, the space between particles was being created so rapidly that everything was carried apart at effectively superluminal speeds. It's like two ants on a rubber band. They're not walking apart. But if you stretch the rubber band fast enough, they separate faster than either of them could ever crawl. Here's the thing about inflation. It wasn't just some wild theoretical speculation cooked up to sound impressive. It was proposed to solve real concrete problems with the standard Big Bang picture. And the person who first put the idea together in a coherent way was a young physicist named Alan Guth, working at Stanford's Linear Accelerator Center in the winter of 1979. Guth was not a cosmologist. That's important. He was a particle physicist interested in things like magnetic monopoles, these hypothetical particles that carry a single magnetic charge, a north without a south, or a south without a north. Grand unified theories of particle physics predicted that the early universe should have produced enormous numbers of these monopoles. But nobody had ever found one. Not a single magnetic monopole had ever been detected, despite serious efforts. So where were they? Guth was puzzling over this one evening, working through the math of how the early universe's phase transitions might have played out, and he realized something. If the universe had undergone a brief period of extraordinarily rapid expansion very early on, before the monopoles had a chance to spread out and populate everything, then the density of monopoles would have been diluted to essentially zero. They'd still exist in principle, but they'd be so fantastically rare that you'd never expect to find one in our observable universe. Inflation would have swept them away, thinned them out like a single drop of ink in an ocean that suddenly became 1,000,000 times larger. And that was exciting. But it was just the beginning, because Guth quickly realized that this same inflationary period solved two other enormous puzzles that had been nagging cosmologists for decades. The first is called the horizon problem. Here's what it boils down to. When you look at the cosmic microwave background radiation, and we'll talk much more about that later, because it's one of the most beautiful pieces of evidence in all of science, you see that the temperature of the universe is almost perfectly uniform in every direction. The differences are tiny, on the order of 1 part in 100,000. But here's the puzzle. Regions of the universe on opposite sides of the sky are so far apart that, in the standard Big Bang model without inflation, they could never have been in contact with each other. Light from one side hasn't had time to reach the other side, even in nearly 14 billion years. So how do they know to be the same temperature? It's as if you walked into a room and found 2 cups of coffee at exactly the same temperature, down to 1,000th of a degree, but the 2 cups had never been in the same building. How would that happen? Inflation solves this beautifully. Before inflation, the entire observable universe was contained in a region so microscopically small that everything within it was in thermal contact. Everything could communicate, exchange energy, reach equilibrium. Then inflation happened, and that tiny, uniform patch was stretched to enormous scales. The uniformity we see today is a relic of that pre-inflationary contact. Those 2 opposite sides of the sky were neighbors once, huddled together in a space smaller than an atom, and inflation pulled them apart. The second puzzle is the flatness problem. Observations tell us that the geometry of the universe is very, very close to flat. Not curved like a sphere, not curved like a saddle. Flat, like an infinite tabletop, at least on the largest scales we can measure. Now, in general relativity, the curvature of the universe is related to its energy density. And the thing is, a flat universe is an unstable condition in the standard Big Bang model. Even the slightest deviation from perfect flatness in the early universe would have been amplified over time. If the universe were even slightly more dense than the critical value, it would have collapsed back on itself long ago. Slightly less dense, and it would have expanded so fast that no galaxies, no stars, no planets could ever have formed. For the universe to be as flat as we observe it today, its density at 1 second after the Big Bang would have had to be tuned to the critical value to within about 1 part in 10 to the 15th power. That's a level of fine-tuning that makes physicists deeply uncomfortable, because in physics, when you see extreme fine-tuning, it usually means you're missing something. Inflation explains this too. Think of it this way. Imagine the surface of a balloon. If the balloon is small, you can see that it's curved. But if you inflate that balloon to an absolutely enormous size, the size of the Earth, say, then any small patch of its surface looks flat. You can't detect the curvature anymore because it's been stretched so far. That's what inflation does to the geometry of the universe. Whatever curvature existed before inflation, the exponential expansion stretched it out so thoroughly that the observable universe, the part we can see, appears flat. It doesn't mean the universe is truly perfectly flat in some absolute mathematical sense. It means that inflation drove it so close to flatness that we can't measure the difference. Guth wrote in his notebook that night, and this is a real detail, you can see it in photographs of the actual page. He wrote, "Spectacular realization," and drew a double box around it. He knew he was onto something big. And he was right, though his original model had some technical problems. The way inflation ended in his version produced a universe that was too lumpy, too inhomogeneous. The phase transition that ended inflation happened in bubbles, like water boiling, and the bubbles didn't merge smoothly enough to give you a uniform cosmos. But within a few years, other physicists refined the idea. Andrei Lind in the Soviet Union, working somewhat independently, developed what he called chaotic inflation. Paul Steinhardt and Andreas Albrecht at the University of Pennsylvania came up with a version called new inflation. These models tweaked the details of the inflationary field, called the inflaton field, so that inflation ended more gracefully, with the field slowly rolling down a potential energy hill rather than tunneling abruptly between states. The result was a universe that, after inflation, was spectacularly smooth and flat on large scales, but with tiny quantum fluctuations baked into it. And those fluctuations, here's where it gets really beautiful, those quantum fluctuations, stretched to macroscopic scales by inflation, became the seeds of all the structure in the universe. Every galaxy, every cluster of galaxies, every vast cosmic web of filaments and voids that you see in surveys of the large-scale universe. All of it traces back to quantum jitters in the inflaton field, magnified to cosmic proportions. Think about what that means. The largest structures in the universe, superclusters of galaxies spanning hundreds of millions of light years, have their origins in quantum mechanics, in the uncertainty principle, in the irreducible fuzziness of nature at the smallest scales. Inflation took the quantum and made it cosmic. That's not poetry. That's what the math says, and it's been confirmed by precision measurements of the cosmic microwave background that match the predicted pattern of fluctuations to extraordinary accuracy. Now, inflation itself lasted an almost inconceivably brief time, somewhere around 10 to the minus 32 seconds, maybe a little more, maybe a little less. The details depend on which model you use, and there are many competing models. But when it ended, something had to happen to all that energy stored in the inflaton field. The field had been driving the exponential expansion, and when it finally rolled down to the bottom of its potential energy curve, that energy didn't just disappear. It was converted, dumped, really, into a blazing hot fireball of particles and radiation. This is called reheating, and it's essentially the moment when the universe, as we usually think of it, begins. The hot, dense, particle-filled cosmos that the classic Big Bang picture describes, that's what emerged from the end of inflation. In a sense, inflation set the stage and then handed things off. And what a stage it was. After reheating, the universe was a plasma again, fantastically hot, fantastically dense, filled with quarks and gluons and electrons and photons and neutrinos and all manner of exotic particles, all colliding and annihilating and being created in an endless frenzy. The temperature was somewhere around 10 to the 27th Kelvin or so, and it was dropping fast as expansion continued. And as it dropped, the universe passed through a series of critical thresholds. Each one was like a fork in the road, a moment where the cooling cosmos made a choice, or rather, where the laws of physics, as they crystallized out of that primordial symmetry, dictated what would happen next. The first of these thresholds that we can describe with real confidence involves the strong nuclear force, and what happened there is something called quark confinement. And it's one of those things that sounds incredibly abstract until you realize it's the reason you have a body at all. So here's what was happening. At those absurd temperatures right after reheating, the universe was filled with a kind of soup that physicists call a quark-gluon plasma. Quarks are the fundamental building blocks that make up protons and neutrons, and gluons are the particles that carry the strong nuclear force. They're literally the glue, which is where the name comes from. At temperatures above roughly 2 trillion Kelvin, 2 times 10 to the 12, quarks and gluons exist freely. They're zipping around independently, not bound to anything, just this roiling, seething broth of fundamental particles. It's a state of matter that doesn't exist naturally anywhere in the universe today, or at least, it hasn't existed naturally since this very moment we're talking about, roughly a microsecond after the end of inflation. But as the universe expanded and cooled, it crossed that 2 trillion Kelvin threshold, and something irreversible happened. The strong force, which had been there all along but couldn't get a grip on anything because everything was too hot and too energetic, suddenly became dominant at the scales that mattered. Quarks couldn't remain free anymore. The strong force pulled them together into bound states, into composite particles called hadrons. And the most important hadrons, the ones that would go on to matter for, well, everything, were protons and neutrons. Each proton is made of 2 up quarks and 1 down quark. Each neutron is 2 down quarks and 1 up quark. And once the temperature dropped enough for these combinations to be stable, quarks were locked away inside them, and they've been locked away ever since. Every proton in your body right now contains quarks that were confined during this transition, roughly a millionth of a second into the life of the universe. That's a thought worth sitting with. Now, this era, the first few microseconds, is also when something else extraordinary was playing out. And it's one of the deepest, unsolved puzzles in all of physics. It's called baryogenesis, and it's the question of why there's any matter at all. See, when the universe was creating particles from pure energy during and right after reheating, it should have created equal amounts of matter and antimatter. That's what the equations predict. Every time you make a quark, you should also make an antiquark. Every electron should come paired with a positron. And when matter and antimatter meet, they annihilate each other completely, converting back into pure energy, photons. So if everything had been perfectly symmetric, all the matter and all the antimatter would have annihilated, and you'd be left with a universe full of nothing but light, no atoms, no stars, no planets, no you. But obviously, that didn't happen. We're here. The universe is full of matter and essentially devoid of antimatter. So somewhere in that first fraction of a second, something tipped the balance. Some process, some slight asymmetry in the laws of physics, favored matter over antimatter by the tiniest amount. The estimates suggest the imbalance was about 1 part in a billion. For every billion antimatter particles, there were 1,000,000,001 matter particles. The billion pairs annihilated each other, and that one leftover particle in every billion. That's everything. Every galaxy, every star, every atom in your body is descended from that tiny surplus. And we still don't fully understand what caused it. We know the general conditions that are required. A Russian physicist named Andrei Sakharov laid them out in 1967. You need processes that violate something called baryon number conservation. You need violations of certain symmetries called C and CP symmetry. And you need the whole thing to happen out of thermal equilibrium. The standard model of particle physics actually contains hints of all three, but not enough. Not nearly enough to explain the magnitude of the asymmetry we observe. So there's almost certainly new physics hiding in this moment, physics we haven't discovered yet. And that's humbling, honestly. We can describe the universe from a microsecond onward with remarkable precision, but the reason anything exists at all, that's still an open question. Anyway, let's keep moving through this cooling universe because things are happening fast. Well, fast by human standards. By the universe's standards, each of these transitions is an eternity of particle interactions. After the quarks were confined into protons and neutrons, the next major event comes at about 1 second after the Big Bang. 1 second. And what happens at the 1 second mark is that neutrinos decouple. Neutrinos are these ghostly, almost massless particles that interact only through the weak nuclear force and gravity. They're famously difficult to detect. Right now, as you lie there, about 65 billion neutrinos from the sun are passing through every square centimeter of your body every second, and they almost never interact with anything. They just sail right through you, through the Earth, through everything. But in the very early universe, when densities and temperatures were extreme enough, even neutrinos were in constant contact with everything else. They were colliding, scattering, participating in the thermal bath like everyone else. At about 1 second in, the temperature dropped to roughly 10 billion Kelvin, 10 to the 10. And the expansion rate of the universe finally outpaced the rate of weak interactions. The neutrinos effectively stopped talking to everything else. They decoupled, went their own way, and have been streaming freely through the cosmos ever since. There should be a cosmic neutrino background out there right now, analogous to the cosmic microwave background, but made of neutrinos instead of photons, and it would carry information about the universe at 1 second old. We haven't been able to detect it yet. Neutrinos are just too elusive, but it's one of the great observational targets for future physics. And here's the thing. Right around this same moment, at about 1 second in, with temperatures around 10 billion Kelvin, something critical was being decided. The ratio of protons to neutrons. See, protons and neutrons can convert into each other through weak interactions. A proton can absorb an electron and become a neutron, or a neutron can decay into a proton by emitting an electron and an antineutrino. At very high temperatures, these reactions happen constantly, in both directions, and they keep the numbers of protons and neutrons roughly equal. But neutrons are slightly heavier than protons, just a tiny bit, about 0.1% heavier. And that tiny mass difference means that as the temperature drops, it becomes slightly harder to make neutrons than protons. The balance tips. By the time the weak interactions freeze out at about 1 second, the ratio has settled to roughly 1 neutron for every 6 protons. And then neutrons, being unstable on their own, start to slowly decay. A free neutron has a half-life of about 10 minutes. So the clock is ticking. Those neutrons need to find their way into stable atomic nuclei before they all decay away, or else the universe will end up with nothing but hydrogen, just lone protons, and the cosmos would be a very different, much simpler, much less interesting place. This is where we arrive at one of the great triumphs of modern cosmology: Big Bang nucleosynthesis. And the story of how we figured it out is almost as good as the physics itself. The key figure here is George Gamow. He was a Ukrainian-born physicist who defected from the Soviet Union in the 1930s and ended up in the United States. And he was one of those irrepressibly creative, slightly wild characters that physics seems to produce every now and then. Gamow had a gift for seeing the big picture. He was also famous for his sense of humor. He once added the name of his friend, Hans Bethe, to a paper he wrote with his student Ralph Alpher, purely so the author list would read Alpher, Bethe, Gamow, like alpha, beta, gamma. The paper was published on April 1st, 1948, which may or may not have been a coincidence. But the content of that paper, the Alpher-Bethe-Gamow paper, was serious and profound. Alpher and Gamow argued that the light elements, hydrogen, helium, and traces of lithium, were forged in the first few minutes of the universe's existence, when the whole cosmos was essentially a nuclear reactor. The idea was that the temperatures and densities in the early universe were high enough for nuclear fusion to occur, but only for a brief window. And this is exactly right. Here's how it works. Starting at about 10 seconds after the Big Bang, with the temperature around 3 billion Kelvin, protons and neutrons began to combine. The first step is the simplest. One proton and one neutron fuse to form deuterium, which is a heavy isotope of hydrogen. But deuterium is fragile. At temperatures above about 1 billion Kelvin, photons are energetic enough to blast deuterium nuclei apart as fast as they form. This is called the deuterium bottleneck, and it's a crucial detail. Nucleosynthesis can't really get going until the universe cools below this threshold, which happens at about 3 minutes in. 3 minutes. Think about that. The universe is 3 minutes old, and only now can you start building anything more complex than a single proton or neutron. Once the bottleneck breaks, things happen fast. Deuterium nuclei start combining with more protons and neutrons to form helium-3 and tritium, and those quickly fuse into helium-4, which is the common, stable form of helium. 2 protons, 2 neutrons, beautifully bound together, and helium-4 is where most of the action stops. Why? Because there's no stable nucleus with 5 nucleons. There's no stable combination of 5 protons and neutrons, and there's no stable nucleus with 8 nucleons either. These gaps, the mass 5 and mass 8 gaps, act as a bottleneck that prevents nucleosynthesis from building heavier elements in any significant quantity. A tiny amount of lithium-7 gets made and traces of beryllium. But that's about it. By about 20 minutes after the Big Bang, the temperature and density have dropped too low for any further nuclear reactions, and nucleosynthesis is over. Done. In those 17 or so minutes of active fusion, the universe produced roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. And here's what's remarkable. We can measure the abundances of these light elements in the oldest, most pristine environments in the universe, in ancient gas clouds that have never been processed through stars, and the numbers match. They match the predictions of Big Bang, nucleosynthesis with extraordinary precision, the helium fraction, the deuterium abundance, even the lithium. Well, actually, lithium is a bit of a headache. There's a persistent discrepancy called the cosmological lithium problem, where we observe about 3 times less lithium-7 than the models predict, and nobody's entirely sure why. It might be a measurement issue. It might be that some process destroyed lithium in stars, or it might be a hint of new physics. But the overall agreement, especially for hydrogen, deuterium, and helium, is one of the strongest pieces of evidence that the Big Bang model is fundamentally correct. It's not just a nice story. It's a quantitative, testable, confirmed prediction. Now, after nucleosynthesis ends at about 20 minutes, the universe enters a long, comparatively quiet stretch. The drama of the first few minutes is over. The cast of characters is set. You've got your hydrogen, your helium, your photons, your neutrinos streaming freely, your electrons, and a mysterious something called dark matter that we haven't really talked about yet, but that was already there, already exerting its gravitational influence. And all of these are embedded in a plasma that's still far too hot for atoms to form. Electrons are still free, not bound to nuclei. And because free electrons are extraordinarily good at scattering photons, the universe is opaque. Light can't travel in a straight line. It's like being inside an incredibly dense, glowing fog. Every photon takes a step, hits an electron, bounces in a random direction, takes another step, hits another electron. The universe is bright, but you can't see through it. And this state of affairs, this hot, opaque, foggy plasma, is going to persist for a very long time by the standards of what we've been discussing. Not microseconds, not minutes, but hundreds of thousands of years. The universe is expanding, cooling, and waiting for the next great threshold, the moment when it finally becomes transparent, when light breaks free for the first time and begins its journey across the cosmos. A journey that ends billions of years later as a faint whisper of microwave radiation that 2 radio astronomers in New Jersey would accidentally stumble upon in 1964 using a large horn antenna at Bell Labs in Holmdel, New Jersey that had been built for satellite communication. Arno Penzias and Robert Wilson. 2 guys who weren't looking for the origin of the universe at all. They were trying to do radio astronomy, calibrating their antenna for something else entirely, and they kept picking up this persistent, low-level noise. A faint hiss. It was coming from everywhere. Not from New York City, not from the sun, not from our galaxy. Everywhere they pointed the antenna, there it was. The same gentle hum, the same faint warmth, uniform across the entire sky. They spent months trying to get rid of it. They checked every connection. They rebuilt parts of the antenna. There's a famous detail in this story. Pigeons had been nesting inside the horn of the antenna, and Penzias and Wilson actually cleaned out the pigeon droppings, thinking maybe that was causing the signal. It wasn't. The noise persisted. It was maddening, because they were meticulous experimentalists, and they could not account for this background hiss no matter what they did. Meanwhile, just 30 miles away at Princeton University, a team led by Robert Dickey and Jim Peebles had been working on a theoretical prediction. They had independently reasoned, building on ideas that went back to Gamow and Alpher in the late 40s, that if the universe really did begin in a hot, dense state, then the light released when the universe first became transparent should still be out there. It would have been stretched by the expansion of space over billions of years, redshifted from its original visible and infrared glow all the way down into the microwave part of the spectrum. And it should look like thermal radiation, the kind of smooth, featureless glow that any hot object emits, with a temperature of just a few degrees above absolute zero. They were actually building their own antenna to look for it. And then someone connected the 2 groups. The story goes that Penzias mentioned the mystery noise to a colleague who mentioned it to someone else who knew what Dickey's group was working on. When Dickey got the phone call, he reportedly turned to his colleagues and said, "Well, boys, we've been scooped." Penzias and Wilson had found it. They'd found the cosmic microwave background, the afterglow of the Big Bang, completely by accident. Let's slow down and really think about what this signal is, because it's one of the most remarkable things in all of science. Remember that hot, opaque plasma we were just talking about? That fog of free electrons and nuclei and photons, all tangled up together, with light unable to travel freely? That state persisted for about 380,000 years after the Big Bang. During all that time, the universe was expanding and cooling. And then, when the temperature dropped to roughly 3,000 Kelvin, about the temperature of the surface of a cool red star, something critical happened. The universe cooled enough for electrons to finally be captured by nuclei. Hydrogen nuclei, which are just protons, grabbed electrons and became neutral hydrogen atoms. Helium nuclei grabbed their electrons too. This process is called recombination, which is actually a slightly misleading name because it implies the electrons and nuclei had been combined before and were recombining. They hadn't. This was the first time. But the name stuck, as names often do in physics. And here's what matters. Once the electrons were bound into atoms, they were no longer free to scatter photons. Suddenly, from the photon's perspective, the universe went from opaque to transparent. The fog cleared. Light could finally travel in a straight line. And those photons, the ones that had been bouncing around in that plasma for hundreds of thousands of years, were released, set free. They began streaming across the universe, and they've been traveling ever since. That's what Penzias and Wilson detected, those exact photons. Well, not the exact individual photons in a quantum mechanical sense, but that same radiation field, that thermal glow from the moment the universe became transparent. It's been traveling for about 13.8 billion years, stretched by the expansion of space from a temperature of roughly 3,000 Kelvin down to about 2.725 Kelvin. Just a whisper above absolute zero. And it fills the entire universe, coming from every direction, because no matter where you look, you're looking back toward that moment when the fog cleared. Think about that for a second. When you tune an old analog television to a channel with no signal and you see that static, that snow on the screen, a small fraction of that noise, maybe 1 or 2%, is actually caused by photons from the cosmic microwave background. You've been watching the afterglow of creation without knowing it. Penzias and Wilson won the Nobel Prize in Physics in 1978 for their discovery. But the story of the cosmic microwave background was really just beginning, because the initial detection told you it was there, and it was roughly the right temperature. But the truly extraordinary science would come from studying it in detail. And here's where it gets really interesting. If the universe had been perfectly smooth, perfectly uniform, no variations at all, then the cosmic microwave background would look exactly the same in every direction. Same temperature, same intensity, completely featureless. And for a long time, that's pretty much what it looked like. Early measurements showed it was astonishingly uniform. The temperature was the same to better than 1 part in 1,000, no matter where you looked, which was itself a triumph for the Big Bang model, because a thermal spectrum that uniform is exactly what you'd expect from a universe that was once in thermal equilibrium. But there was a puzzle lurking here, and it connects back to something we talked about earlier. Inflation. Remember the horizon problem? The question of how regions of the universe that seem too far apart to have ever been in contact could have the same temperature? Inflation solved that by proposing that everything was once in contact, in a tiny patch, before being stretched apart. The uniformity of the CMB is actually evidence for something like inflation having occurred. But here's the thing, perfect uniformity would be a disaster. Because we exist. Galaxies exist. Stars exist. Planets exist. All of that structure requires that the early universe was not perfectly smooth. There had to be tiny variations, slightly denser regions and slightly less dense regions that could later grow under gravity into the cosmic web of galaxies and clusters we see today. And those tiny variations should be imprinted on the cosmic microwave background as minuscule temperature differences. Slightly hotter spots where the plasma was slightly denser, slightly cooler spots where it was slightly less dense. The search for these tiny fluctuations became one of the great quests in cosmology. And it was hard. We're talking about temperature differences of roughly 1 part in 100,000. Incredibly small. You need exquisitely sensitive instruments, and you need to get above Earth's atmosphere, which emits its own microwave radiation and messes everything up. The breakthrough came in 1992 with NASA's COBE satellite, the Cosmic Background Explorer. COBE had been launched in 1989, and its team, led by John Mather and George Smoot, spent years carefully analyzing the data. When they finally released their results, it was a bombshell. First, the FIRIS instrument on COBE measured the spectrum of the CMB with incredible precision and found that it was a perfect blackbody, the most perfect thermal spectrum ever measured in nature. This was the spectrum of something that was once in perfect thermal equilibrium, exactly as predicted. John Mather would later describe showing this result at a conference and receiving a standing ovation, which is not something that happens often in physics. And then the DMR instrument on COBE detected the fluctuations, the tiny, tiny temperature variations across the sky. 1 part in 100,000. They were there. George Smoot famously described seeing them as like looking at the face of God, which is a dramatic thing to say, but honestly, in context, you can understand the emotion. These ripples in the CMB are the seeds of all structure in the universe. Every galaxy, every star, every planet, every person, all of it traces back to those quantum fluctuations, stretched to cosmic scales by inflation, imprinted on the microwave background, and then amplified by gravity over billions of years. Mather and Smoot shared the Nobel Prize in Physics in 2006 for this work. But COBE was just the beginning. Its resolution was fairly coarse. It could see the big features, but not the fine details. The next generation came with 2 extraordinary missions. First was WMAP, the Wilkinson Microwave Anisotropy Probe, launched by NASA in 2001 and named after David Wilkinson, a Princeton cosmologist who had been part of Dickey's original group back in the 60s and who sadly died before the mission produced its results. WMAP mapped the CMB with far greater resolution and precision than COBE, and its data allowed cosmologists to extract an astonishing amount of information about the universe. Here's what's so clever about this. The pattern of hot and cold spots in the CMB isn't random. It has a statistical structure. Certain sizes of spots are more common than others. When you analyze the pattern mathematically, breaking it into its component frequencies the way you might break a musical chord into its individual notes, you get what's called the power spectrum. And the shape of that power spectrum depends on the fundamental properties of the universe, its total density, its composition, its geometry, how fast it's expanding. By fitting theoretical models to the observed power spectrum, you can measure these cosmic parameters with remarkable precision. And then came Planck. The European Space Agency's Planck satellite, launched in 2009, pushed the precision even further. The maps from Planck are breathtaking in their detail. Millions of tiny temperature variations across the entire sky, each one telling you something about the conditions in the universe 380,000 years after the Big Bang. From Planck's data, we know that the universe is 13.8 billion years old, give or take about 40 million years. We know that ordinary matter, the stuff you and I are made of, atoms, the periodic table, everything you can see and touch, makes up only about 5% of the total energy content of the universe. About 27% is dark matter, that mysterious something we keep mentioning but haven't explained yet. And the remaining 68% is something even stranger, called dark energy. Let those numbers sit for a moment. Everything you have ever seen, every star in every galaxy, every planet, every grain of sand, every molecule in your body, all of it is 5% of what's out there. The rest is dark, hidden, invisible to every telescope we've ever built, detectable only through its gravitational effects and its influence on the expansion of the universe. Now, dark matter. We should finally talk about dark matter, because it's been lurking in our story from the very beginning, exerting its pull, shaping the universe, and we've been politely stepping around it. The evidence for dark matter goes back surprisingly far, to the 1930s actually, and a brilliant, cantankerous, sometimes genuinely difficult Swiss-American astronomer named Fritz Zwicky. Zwicky was working at Caltech, studying galaxy clusters, huge collections of galaxies bound together by gravity. And he noticed something that didn't add up. When he measured how fast the galaxies in the Coma cluster were moving, they were moving far too fast. Given the amount of visible matter he could see, the stars, the gas, there wasn't nearly enough gravity to hold the cluster together. The galaxies should have been flying apart. He calculated that there had to be about 400 times more mass than what was visible. He called it dunkle materie, dark matter, and then most people ignored him for about 40 years, partly because the results seemed too extreme, and partly because Zwicky had a reputation for being, let's say, abrasive. He reportedly called some of his colleagues spherical bastards, because they were bastards no matter which direction you looked at them from. But the evidence kept building, and the person who really brought dark matter into the mainstream of astronomy was Vera Rubin, working with Kent Ford at the Carnegie Institution in the 1970s. Rubin was measuring the rotation curves of spiral galaxies, how fast stars orbit at different distances from the galactic center. Now, if most of a galaxy's mass were concentrated in the bright central region, which is what it looks like, then you'd expect stars farther out to orbit more slowly. Just like the outer planets in our solar system orbit the sun more slowly than the inner ones. That's just Kepler's laws, basic orbital mechanics. But that's not what Rubin found. She found that stars at the edges of galaxies were orbiting just as fast as stars closer to the center. The rotation curves were flat. And the only way to explain that was if each galaxy was embedded in an enormous halo of invisible mass that extended far beyond the visible stars and gas, mass that you couldn't see but that was unmistakably there, shaping everything. Rubin's galaxies were spinning in a way that only made sense if they were cradled inside these vast, invisible cocoons of something heavy and dark, something that outweighed the visible stars and gas by a factor of 5 or 6 to 1. And what made her work so compelling wasn't just one galaxy. It was galaxy after galaxy after galaxy. She and Ford observed dozens of spiral galaxies, and the result was always the same: flat rotation curves every single time. This wasn't a fluke. This wasn't an oddity in one weird galaxy. This was universal. And here's the thing that makes Rubin's story particularly poignant. She had faced resistance her entire career, not because her science was weak, but because she was a woman doing astronomy in an era when that was still treated as unusual. She was the first woman allowed to observe at Palomar Observatory in 1965. When she arrived, there was no women's restroom. She reportedly taped a paper skirt onto the stick figure on the men's room door and said, "There you go. Now you have one." That was the kind of person she was: persistent, practical, a little wry, and absolutely determined to let the data speak for itself. And the data spoke loudly. By the late 70s, the astronomical community could no longer wave away dark matter as Zwicky's eccentricity. Rubin had shown it was everywhere. So what is dark matter actually? That's the question, and honestly, as of right now, we still don't have a definitive answer. We know an enormous amount about what dark matter does, how it shapes galaxies, how it bends light, how it guided the formation of cosmic structure. But we don't yet know what it's made of. And that's one of the biggest open questions in all of physics. Let's talk about what we do know. Dark matter doesn't emit light. It doesn't absorb light. It doesn't scatter light. That's why it's dark. It doesn't interact with electromagnetic radiation at all. Or if it does so incredibly weakly. You can't see it with any kind of telescope, whether optical, radio, infrared, ultraviolet, X-ray, or gamma ray. It passes right through ordinary matter like a ghost through a wall. But it has mass, and mass means gravity, and gravity we can detect. One of the most spectacular ways we detect dark matter is through gravitational lensing. Einstein predicted this back in 1915 with general relativity. Mass curves spacetime, and curved spacetime bends the path of light. So, if there's a massive cluster of galaxies between us and some more distant galaxy, the light from that distant galaxy gets bent and distorted as it passes through the cluster's gravitational field. You see arcs, rings, sometimes multiple images of the same background galaxy smeared around the foreground cluster like light through the bottom of a wine glass. And when astronomers map out how much mass is needed to produce the lensing they observe, they consistently find far more mass than what's visible. The dark matter is right there in the math, bending space-time, warping the images of distant galaxies. Another line of evidence comes from the cosmic microwave background itself, those tiny temperature fluctuations we talked about. The precise pattern of peaks and valleys in the CMB power spectrum, the way those fluctuations are distributed across different angular scales, encodes information about the composition of the universe. And the pattern only fits if you include a large component of matter that doesn't interact with light. Ordinary matter, the stuff made of protons and neutrons, what physicists call baryonic matter, leaves a specific signature because it couples to photons. It pushes and gets pushed by light. Dark matter doesn't. It clumps under gravity without being buffeted by radiation pressure, and that difference changes the acoustic peaks in the CMB in a way that's measurable. The data from WMAP and Planck nail this down beautifully. About 27% of the universe's total energy content is dark matter. Only about 5% is ordinary matter. Think about that for a second. Everything you've ever seen, everything you've ever touched, every star, every planet, every person, every atom in your body, all of that is just 5% of what's out there. The rest is something else entirely. So what are the candidates? What could dark matter actually be? The leading idea for decades has been some kind of new subatomic particle. Something not in the standard model of particle physics, something that interacts through gravity and possibly through the weak nuclear force, but not through electromagnetism or the strong force. The most popular class of candidates are called WIMPs, weakly interacting massive particles. The name is a bit of a joke, especially when you contrast it with the other category, MACHOs, which stands for Massive Astrophysical Compact Halo Objects. Astronomers have a sense of humor. WIMPs are appealing for a deep theoretical reason sometimes called the WIMP miracle. If you postulate a particle with a mass roughly in the range of 10 to 1,000 times the proton mass, and it interacts with the strength of the weak nuclear force, then you can calculate how many of these particles would have been produced in the early universe, and how many would survive to the present day as the universe cooled and expanded. And the number you get is remarkably close to the amount of dark matter we actually observe. That coincidence, that a particle with weak scale properties naturally gives you the right abundance, made WIMPs the front runner for years. Huge experiments have been built to try to catch a WIMP in the act of bumping into an ordinary atom. These are some of the most sensitive instruments ever constructed. Deep underground, in old mines and tunnels, shielded from cosmic rays by hundreds of meters of rock, sit tanks of ultra-pure liquid xenon or germanium crystals, cooled to near absolute zero, waiting for the faintest nudge from a passing dark matter particle. Experiments like ELOX, Xenon 1T, PandaX, and their successors have been running for years, and so far, nothing. No confirmed detection. The sensitivity has improved by orders of magnitude, ruling out large swaths of the parameter space where WIMPs were expected to live. That doesn't mean WIMPs are dead, but they're feeling the pressure. Other candidates have been gaining attention. Axions, for instance, hypothetical particles originally proposed in the late 1970s to solve a different problem in particle physics, something called the strong CP problem, which is essentially the question of why the strong nuclear force treats matter and antimatter so symmetrically when it doesn't have to. It turns out that the particle you'd invent to fix that problem would also be produced abundantly in the early universe, would be extremely light, would be stable, and would behave gravitationally, just like cold, dark matter. Experiments like ADMX, the Axion dark matter experiment, are searching for axions by looking for their extremely rare conversion into photons in the presence of a strong magnetic field. It's an incredibly delicate measurement, but the technology is getting there. And then there are more exotic ideas, sterile neutrinos, heavier cousins of the neutrinos we already know about, ones that interact even more weakly. Primordial black holes that formed not from collapsing stars, but from extreme density fluctuations in the very early universe, possibly during inflation. For a while, some physicists wondered if dark matter might not be a particle at all, but rather a sign that our theory of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, can reproduce flat rotation curves without dark matter by tweaking how gravity works at very low accelerations. It's clever, and it works surprisingly well for individual galaxies. But it struggles badly with galaxy clusters and with the CMB. Most cosmologists today think dark matter is real stuff, real particles or objects, not a modification of gravity. But MOND hasn't been completely killed off either. Science is messy like that. Now, here's what's really beautiful about dark matter's role in the story of the universe. Remember those tiny fluctuations in the cosmic microwave background? Those 1 in 100,000 variations in temperature that Kobe first detected? Those fluctuations correspond to slight variations in density. Places where matter was just a little bit more concentrated, and places where it was a little bit less. And dark matter, because it doesn't interact with light, started clumping under its own gravity long before ordinary matter could. During the era before recombination, ordinary matter was locked in that tug-of-war with radiation, the acoustic oscillations we talked about, bouncing back and forth, unable to collapse. But dark matter was free. It didn't feel the radiation pressure. It just quietly gathered, pulled together by gravity, forming a cosmic scaffolding, a web of denser regions connected by filaments, surrounding vast, empty voids. And then, after recombination, when the universe became transparent and ordinary matter was finally released from the grip of the photons, that ordinary matter fell into the gravitational wells that dark matter had already prepared. Like water flowing downhill into valleys that had been carved while it was frozen, the hydrogen and helium gas settled into the dark matter framework. And that's where the first structures began to form. Without dark matter, the universe wouldn't have had enough time to build galaxies. The gravitational seeds from ordinary matter alone were too small, too slow. Dark matter did the heavy lifting, literally, creating the architecture that everything else would be built upon. So when you look up at the night sky and see the Milky Way stretching overhead, you're seeing the visible 5%, the luminous frosting on a cake made almost entirely of something invisible. The galaxy you live in is held together by a halo of dark matter that extends far beyond the farthest stars, a halo that outweighs all the stars and gas and dust and planets combined. But dark matter, as mysterious as it is, isn't even the strangest component of the universe. That distinction belongs to something even more puzzling, something that makes up 68% of everything, something that was only discovered in 1998, and something that shook cosmology to its foundations. It's called dark energy, and the story of how we found it starts with a very specific kind of exploding star and two rival teams of astronomers who were racing each other to measure something they thought they already knew the answer to: how fast the expansion of the universe was slowing down. Because here's the thing. By the late 1990s, cosmologists were pretty confident about one big question. The universe is expanding. We've known that since Hubble. But gravity pulls everything together, right? Every galaxy tugging on every other galaxy, every bit of matter attracting every other bit of matter. So the natural expectation was that the expansion should be decelerating, slowing down over time, like a ball thrown upward gradually losing speed. The only real question was how much it was slowing down and whether it would ever stop completely and reverse, a big crunch, everything collapsing back together, or whether the expansion would just coast along forever, getting slower and slower, but never quite stopping. That was the question these two teams set out to answer. One team was called the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory. He'd been working on this since the late 80s, painstakingly developing techniques to find and measure distant supernova. The other team was the High Z Supernova Search Team, led by Brian Schmidt, a young astronomer working out of Australia, with Adam Rees doing much of the critical data analysis. These two groups were competitors. They were racing to the same finish line, using the same basic method, sometimes even looking at the same patches of sky. And the tool they were using, the specific kind of exploding star, was a Type 1a supernova. Now, let's talk about why Type 1a supernova are so special, because this is genuinely clever. Most explosions in space vary wildly in brightness. A massive star-going supernova can be brighter or dimmer depending on how big the star was, what it was made of, how the explosion played out. But Type 1a supernovae are different. They occur in binary star systems where a white dwarf, that's the dense remnant core of a dead star, roughly the mass of the Sun squeezed into something the size of Earth, is orbiting close to a companion star. The white dwarf gradually siphons matter off its companion, pulling gas onto its surface, growing heavier and heavier. And there's a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of our Sun. When the white dwarf hits that mass, the pressure and temperature at its core become so extreme that carbon fusion ignites catastrophically throughout the entire star, essentially all at once. The whole thing detonates. It doesn't collapse. It's completely destroyed in a thermonuclear explosion so bright it can outshine an entire galaxy for a few weeks. And here's the key. Because the explosion always happens at roughly the same mass, that Chandrasekhar limit, the brightness is remarkably consistent. Not perfectly identical, but close enough that astronomers can calibrate them. After applying corrections based on how quickly the light fades, they become what's called standard candles. You know how bright they actually are. So when you spot one in a distant galaxy, you can compare how bright it appears to, how bright you know it really is, and from that difference, you can figure out how far away it is. It's the same principle as seeing a streetlight in the fog. If you know the wattage of the bulb, the dimmer it looks, the farther away it must be. Combine that distance with the redshift of the galaxy, how much its light has been stretched by the expansion of space, and you can map out the expansion history of the universe. You can see whether the expansion was faster or slower at different epochs. So both teams were out there hunting for Type 1a, supernovae, in very distant galaxies. Galaxies so far away that their light had been traveling for billions of years. They were looking back in time, essentially, trying to see how the expansion rate had changed over cosmic history, and they expected to find deceleration. Everyone expected deceleration. The whole point was to measure how much. By 1997, 1998, both teams had enough data to start drawing conclusions. And this is where the story gets extraordinary, because independently, working with their own data and their own analysis pipelines, both teams found the same thing. And it wasn't deceleration. The distant supernovae were dimmer than they should have been. Not by a huge amount, but consistently, unmistakably dimmer, which meant they were farther away than expected, which meant the universe hadn't been slowing down. It had been speeding up. Think about what that means. Throw a ball straight up in the air, and instead of it slowing down, it accelerates away from you faster and faster. That's not how gravity works. Gravity should be pulling everything together, putting the brakes on expansion. Something was pushing the universe apart, and it was winning. Adam Rees has talked about this moment, about checking and rechecking the numbers, convinced there must be an error somewhere. Saul Perlmutter's team went through the same agonizing process. They looked for systematic errors. Maybe dust was dimming the supernovae, making them look farther away than they really were. Maybe Type 1a supernovae in the early universe behaved differently than nearby ones. They tested everything they could think of, and the result held. The universe's expansion is accelerating. When both teams published their results in 1998 and 1999, the reaction in the physics community was something between shock and excitement. This was not a minor correction to existing models. This was a fundamentally new component of the universe, something with a deeply strange property. It acts like a repulsive force, a kind of anti-gravity that operates on the largest scales. And it was immediately given a name, dark energy, though calling it that doesn't really explain anything. It's a label for our ignorance, honestly, a placeholder for whatever is causing the acceleration. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for this discovery. And it's worth noting that this is one of those rare cases where two competing teams working independently confirmed each other's result. That's about as strong as observational evidence gets. If only one team had found it, you might wonder. But both teams, using slightly different methods and different supernova samples, converging on the same answer. That's compelling. So what is dark energy? And here's where I have to be honest with you. Nobody really knows. That's not a cop-out. It's the actual state of the field. We know what it does. We can measure its effects with remarkable precision. But we don't know what it is. The simplest explanation, and the one that currently fits the data best, goes back to Einstein. Remember how Einstein introduced the cosmological constant, that fudge factor he added to his equations to keep the universe static, which he later regretted? Well, it turns out something very much like the cosmological constant actually exists. In modern terms, you can think of it as the energy of empty space itself. Quantum field theory tells us that even a perfect vacuum isn't truly empty. It's seething with virtual particles popping in and out of existence, and that quantum activity carries energy. If empty space has a constant energy density everywhere, then as the universe expands and creates more space, there's more total energy driving the expansion. The more space you have, the more dark energy there is, the faster the expansion accelerates. It feeds on itself. That sounds elegant, and in some ways it is. But here's the problem. And this is one of the most famous unsolved problems in all of physics. When theorists try to calculate how much energy the quantum vacuum should have, using the standard tools of quantum field theory, they get a number that is roughly 10 to the power of 120 times larger than what we actually observe. That's not off by a factor of 2, or 10, or even a million. It's off by a factor of 1, followed by 120 zeros. It has been called the worst prediction in the history of physics, and that's not really an exaggeration. Something is either deeply wrong with how we calculate vacuum energy, or there's some unknown mechanism that cancels almost all of it out, leaving just the tiny residual amount we observe. Either way, we don't understand it. There are other possibilities beyond the cosmological constant. Some physicists have proposed that dark energy isn't constant at all, that it changes over time, maybe even changes its character. These models go by names like quintessence, where dark energy is actually a dynamic field that evolves as the universe ages. If that's the case, the acceleration we see today might not last forever. It might strengthen or weaken or even reverse. Some of the more dramatic scenarios, like the Big Rip, imagine dark energy growing stronger and stronger until it eventually tears apart galaxies, then solar systems, then planets, then atoms themselves. That's a pretty extreme outcome, and current observations don't particularly favor it, but we can't rule it out either. And this is what makes dark energy so unsettling and so fascinating at the same time. It's the dominant component of the universe, 68% of the total energy budget. And we can describe its behavior mathematically. We can see its fingerprints in the supernova data, in the CMB, in the large-scale distribution of galaxies. The evidence is overwhelming. But the underlying physics remains a mystery. It sits right at the intersection of general relativity and quantum mechanics, the two great pillars of modern physics that have never been fully reconciled with each other. Some people think that understanding dark energy will require a theory of quantum gravity, a framework that unifies Einstein's description of space-time with the quantum world. And we don't have that theory yet. But let's step back from the mystery for a moment and appreciate what we do know. Because the picture that emerges when you put all the pieces together is genuinely remarkable. We've got a universe that's 13.8 billion years old, expanding and accelerating, made of roughly 5% ordinary matter. The atoms, the protons and neutrons, the stuff of stars and planets and you and me. 27% dark matter, that invisible gravitational scaffolding holding galaxies and clusters together, and 68% dark energy. This enigmatic something pushing everything apart faster and faster. And we've measured those proportions with extraordinary precision, cross-checked by multiple independent methods. The CMB, supernova, galaxy surveys, gravitational lensing, the abundance of light elements from Big Bang nucleosynthesis. They all converge on the same picture. Cosmologists call it the lambda CDM model. Lambda for the cosmological constant representing dark energy, CDM for cold dark matter, and it's the standard model of cosmology. It works astonishingly well. And yet, within that success, there are tensions, cracks that might be nothing, or might be hints of something deeper. One of the most talked about is the Hubble tension, a disagreement between two different ways of measuring how fast the universe is expanding right now. If you use the CMB data, the Planck satellite's exquisitely detailed map of the early universe, and you run the lambda CDM model forward to predict today's expansion rate, you get a value of about 67.4 kilometers per second per megaparsec. But if you measure the expansion rate directly, using the cosmic distance ladder, Cepheid variable stars calibrating type 1a supernovae in nearby galaxies, working your way outward step by step, you get a higher number, around 73. And both measurements have gotten more and more precise over the years, which means the disagreement has gotten more and more statistically significant. It's not a small discrepancy anymore. Something doesn't quite fit, and nobody is sure whether it's a subtle systematic error in one of the measurements, or whether it's telling us that the lambda CDM model is incomplete, that there's new physics we haven't accounted for. Maybe dark energy isn't quite constant. Maybe there's an extra species of neutrino we haven't detected. Maybe something happened in the early universe that we haven't modeled correctly. This is the kind of tension that keeps cosmologists up at night, which is ironic, given that you're trying to fall asleep. But it's also the kind of tension that has historically led to breakthroughs. When the data doesn't quite fit the model, that's not a failure. That's an invitation. And right now, a new generation of instruments is coming online that might resolve it, or might deepen the mystery even further. Telescopes like the James Webb Space Telescope, which launched in late 2021, and the Euclid mission, launched by the European Space Agency in 2023, designed specifically to map the geometry of the universe and probe the nature of dark energy by surveying billions of galaxies across vast stretches of cosmic time, and ground-based surveys like the Vera C. Rubin Observatory, named beautifully after the astronomer whose rotation curves made the case for dark matter, which will photograph the entire visible sky every few nights, building up the most detailed map of the universe ever constructed. These instruments are going to generate an almost incomprehensible flood of data over the next decade. And somewhere in that data, there might be answers to questions we've been asking for a quarter century. What is dark energy? Is it truly constant, or is it evolving? Is the Hubble tension real, and if so, what's causing it? And there's an even deeper question lurking beneath all of this, one that connects back to the very beginning of our story, back to that first fraction of a second when the universe inflated by a factor so enormous that the numbers barely make sense, when quantum fluctuations got stretched across the sky and became the seeds of everything. Because here's what's fascinating. When we look at the biggest unsolved problems in cosmology today, so many of them trace back to that moment. Dark energy, dark matter, the Hubble tension, the matter-antimatter asymmetry. They're all, in one way or another, questions about what happened in the first sliver of time. And that means the story of the universe isn't just a story that moves forward from the Big Bang to now. It's also a story that keeps circling back, keeps returning to the beginning, because the beginning is where the answers are buried. So let's do that. Let's circle back one more time, but with everything we've learned along the way, because now you know enough to appreciate just how remarkable the whole picture is. Think about where we started. Not the beginning of the universe, the beginning of our understanding of it. A century ago, most scientists thought the universe was static, eternal, unchanging. Einstein himself was so committed to that idea that he added a fudge factor to his equations to prevent them from predicting expansion. And then Lemaître came along, this quiet Belgian priest with a PhD in physics, and said, no, the equations are telling us something real. The universe is expanding, and if you run the clock backward, everything converges to a single point, a single moment of creation. He called it the primeval atom. People thought he was letting his theology contaminate his physics, but he was right, and Hubble's observations confirmed it. And then decades later, Penzias and Wilson stumbled onto the afterglow of that moment, the cosmic microwave background, that faint hiss of radiation coming from every direction in the sky. And suddenly, the Big Bang wasn't just a theory anymore. It was the only theory that fit the evidence. And then the picture got richer. Gamow and Alpher worked out what should have happened in those first few minutes. The nuclear furnace of Big Bang nucleosynthesis, protons and neutrons slamming together to forge helium and a tiny bit of lithium. And when we looked at the oldest stars and the most pristine clouds of gas, the abundances matched. 75% hydrogen, 25% helium, just like the theory predicted. Then Guth proposed inflation, and suddenly we had an explanation for why the universe looks so uniform, so flat, so free of magnetic monopoles. And COBE and WMAP and Planck mapped the cosmic microwave background with increasing precision and found exactly the pattern of tiny temperature variations that inflation predicted, the fingerprints of quantum fluctuations stretched across the sky. And then Zwicky's crazy idea about missing mass turned out to be right, and Rubin's rotation curves proved it, and we realized that most of the matter in the universe is invisible, this dark matter that doesn't interact with light but shapes the gravitational scaffolding on which galaxies form. And then Perlmutter and Schmidt and Rees discovered that the expansion of the universe isn't just continuing, it's accelerating, driven by this mysterious dark energy that makes up nearly 70% of everything. And all of that, all of it, fits together into a single coherent model. Lambda CDM, 5% ordinary matter, 27% dark matter, 68% dark energy. A universe that began 13.8 billion years ago, inflated wildly, cooled, formed atoms, released light, collapsed into structures under gravity, and is now flying apart faster and faster. That's the story. And it's extraordinary. But here's the thing. It's also, in some ways, deeply unsatisfying. Because for all the precision of lambda CDM, for all the decimal places in the Planck data, we still don't know what most of the universe actually is. We don't know what dark matter is made of. We don't know what dark energy is. We don't know why there's more matter than antimatter. We don't know whether inflation really happened the way we think it did, or what caused it, or what the inflaton field actually is. We have a model that fits the data beautifully, but the model is full of placeholders. It's like having a map that's incredibly detailed and accurate, but where 70% of the territory is labeled, "Here be dragons." And that's not a criticism. That's the honest state of the science. And it's worth sitting with that for a moment, because it tells you something important about how science actually works. We don't arrive at final answers. We arrive at better questions. Every breakthrough in cosmology, Hubble's expansion, the CMB, dark matter, dark energy, each one solved a problem and simultaneously revealed a deeper one. The universe keeps peeling back layers, and every layer is stranger than the last. Let me give you a concrete example of how this plays out. Take the question of what happened before inflation. Now, in one sense, this question might not even be well defined. If inflation created space and time as we know them, then asking what came before might be like asking what's north of the North Pole. The question assumes a framework that doesn't apply. But physicists can't help themselves. They want to push further. And there are ideas. One of the most intriguing is the multiverse hypothesis. The idea, which grows naturally out of certain versions of inflation theory, particularly eternal inflation, which Alan Guth and Andre Linde explored, is that inflation might not have stopped everywhere at once. In our region of space, inflation ended. The energy of the inflaton field converted into matter and radiation, and the hot Big Bang began. But in other regions, inflation might have continued, spawning new pocket universes, each with its own Big Bang, its own physical constants, maybe even its own laws of physics. In this picture, our observable universe, everything we can see, all 13.8 billion light-years of it, is just one bubble in an infinite, ever-expanding foam of universes. Now you might be thinking, that sounds more like science fiction than science. And honestly, a lot of physicists feel the same way. The problem with the multiverse is that it might be fundamentally untestable. If these other universes are causally disconnected from ours, if no signal can ever travel between them, then how would we ever know they exist? And if we can't test the idea, is it really science? This is one of the deepest philosophical debates in modern cosmology, and smart people come down on both sides. Some, like Leonard Susskind and Max Tegmark, argue that the multiverse is a natural prediction of our best theories, and we shouldn't reject it just because it's hard to test directly. Others, like Paul Steinhardt, who, remember, helped develop inflation in the first place, have become deeply skeptical, arguing that a theory that can predict anything effectively predicts nothing. It's a genuinely fascinating argument, and it gets at something fundamental about what we want from science. Do we want a theory that explains why the universe is the way it is? Or are we willing to accept a theory that says, well, every possible universe exists, and we just happen to be in this one because this one supports the existence of beings who can ask the question? That second idea, the anthropic principle, is either a profound insight or a cop-out, depending on who you ask. But let's come back to things we can actually measure, because there's plenty of mystery right here in our own universe. One of the most exciting frontiers right now is gravitational wave astronomy. When Einstein published his general theory of relativity in 1915, he predicted that massive accelerating objects, like two black holes spiraling toward each other, would create ripples in the fabric of space-time itself. He was right. But he also thought we'd never be able to detect them, because the effect is so incredibly tiny. A gravitational wave passing through Earth might stretch or compress the planet by less than the width of a proton. How do you measure something that small? It took 100 years, but in September of 2015, the LIGO detectors, two enormous laser interferometers, one in Louisiana and one in Washington state, each with arms 4 kilometers long, picked up a signal, a chirp, a tiny wobble in their laser beams that lasted less than a second. And when they analyzed it, they found it matched the predicted signature of two black holes, each about 30 times the mass of the Sun, spiraling together and merging, releasing more energy in that final fraction of a second than all the stars in the observable universe combined. The announcement came in February of 2016, and it was one of those moments where the entire physics community just stopped and marveled. Rainer Weiss, Kip Thorne, and Barry Barish shared the 2017 Nobel Prize for it. But here's why this matters for cosmology, not just astrophysics. Gravitational waves give us a completely new way to observe the universe. Everything we've talked about so far, Hubble's observations, the CMB, supernovae, galaxy surveys, all of that uses light, electromagnetic radiation. Gravitational waves are different. They're not light. They're vibrations in space-time itself, and they can carry information from places and times that light can't reach. The very early universe, for instance, was opaque to light. Photons couldn't travel freely until recombination, 380,000 years after the Big Bang. But gravitational waves could have traveled freely from the very first moments. If we could detect primordial gravitational waves, ripples generated during inflation itself, we'd be looking directly at the universe when it was a tiny fraction of a second old. We'd be seeing, or rather hearing, the birth cry of space-time. And there are experiments trying to do exactly that. The BICEP and Keck Array telescopes at the South Pole are searching for a specific pattern in the polarization of the cosmic microwave background, a swirling pattern called B-mode polarization that would be the imprint of primordial gravitational waves on the CMB. In 2014, the BICEP-2 team announced they'd found it, and for a few breathless weeks, it seemed like we had direct evidence of inflation. But then, it turned out that much of the signal was contaminated by dust in our own galaxy. The result didn't hold up. It was a heartbreaking false alarm. But the search continues with more sensitive instruments and better dust modeling, because if that signal is there, even faintly, it would be one of the most important discoveries in the history of science. It would confirm that inflation happened, pin down the energy scale at which it occurred, and open a window onto physics at energies we could never hope to reach in any particle accelerator on Earth. And that's just one thread. There are others. Experiments hunting for the nature of dark matter in deep underground laboratories, neutrino observatories buried in Antarctic ice, particle colliders searching for supersymmetric particles that might explain the hierarchy problem. There are theorists working on string theory and loop quantum gravity, trying to unify quantum mechanics and general relativity into a single framework that could describe the very first instant of the universe, that Planck epoch before even inflation. when the universe was so small and so hot that our current theories simply break down. We don't have a theory of quantum gravity yet. We don't know what happens when you try to describe space-time itself at the quantum level. But people are working on it. They've been working on it for decades. And someday, maybe not soon, but someday, someone is going to figure it out. And when they do, it might change everything we think we know about how the universe began. But you know what I find most remarkable about all of this? It's not any single discovery. It's the arc. It's the fact that a species of primates on a small, rocky planet orbiting an unremarkable star in the outer suburbs of an ordinary galaxy has managed, through sheer stubbornness and curiosity, to reconstruct the history of the entire cosmos. We've figured out what happened in the first 3 minutes after the Big Bang. We've measured the age of the universe to within a fraction of a percent. We've mapped the afterglow of creation. We've discovered that most of the universe is made of stuff we can't see and driven apart by a force we don't understand. And we're still going. We're still asking questions. We're still building bigger telescopes, more sensitive detectors, more powerful theories. And every answer we find opens up 2 more questions we didn't even know to ask. That's the pattern. That's always been the pattern. And honestly, I think that's the most beautiful thing about it. Think about where we started tonight. We started with you, lying here, breathing, made of atoms that were forged inside stars that exploded billions of years ago. And we traced the story backward, past the formation of those stars, past the first atoms, past the first nuclei, past the moment when the universe was a soup of quarks and gluons so hot that matter as we know it couldn't exist. We went all the way back to inflation, that wild, almost absurdly brief moment when the universe expanded faster than light, smoothing everything out, planting the quantum seeds that would grow into galaxies. And we hit the wall, the Planck epoch, that first sliver of time so unimaginably small, 10 to the minus 43 seconds, where everything we know about physics breaks down and something new, something we haven't figured out yet, must take over. And here's what I want you to sit with, just for a moment. That wall isn't a failure. It's an invitation. Every time in the history of science that we've hit a wall like that, it's meant we were about to learn something profound. When Newton's gravity couldn't explain the orbit of Mercury, it wasn't a dead end. It was a signpost pointing toward Einstein's general relativity. When classical physics couldn't explain why hot objects glow the colors they do, it wasn't a dead end. It was a signpost pointing toward quantum mechanics. The Planck wall is the same kind of thing. It's telling us that there's a deeper layer of reality waiting to be understood, and someone, someday, is going to understand it. But let's not stay at the edge of the unknown. Let's come back to what we do know, because what we do know is extraordinary. Let's just appreciate the full sweep of it for a moment. You live in a universe that is 13.8 billion years old. We know this. We've measured it multiple ways, from the expansion rate, from the cosmic microwave background, from the ages of the oldest stars, and they all converge on the same number, give or take a few tens of millions of years. 13.8 billion years. That's the age of everything. Every atom in your body, every photon of light hitting your window, every galaxy visible through the most powerful telescope ever built. All of it traces back to the same beginning, the same hot, dense state that Lemaître first imagined in 1927 when he talked about the primeval atom. And the universe isn't static. It never was. It's been expanding this whole time, stretching space itself, carrying galaxies apart from one another. Hubble showed us that in 1929. And then, 70 years later, Perlmutter and Schmidt and Rees showed us something even stranger, that the expansion is speeding up. Something is pushing the universe apart, something woven into the fabric of space itself, and we call it dark energy, and it makes up 68% of everything that exists, and we have almost no idea what it is. That's humbling. That's genuinely humbling. More than 2/3 of the universe is a mystery. And then there's dark matter, another 27%, invisible and untouchable, interacting with ordinary matter only through gravity. Zwicky spotted the first clues in the 1930s. Vera Rubin and Kent Ford nailed it down in the 1970s with those beautiful galaxy rotation curves, and we've been hunting for it ever since, in underground labs, in particle colliders, in the sky. We haven't caught it yet, but we know it's there. The evidence is overwhelming, written into the rotation of galaxies, the bending of light, the very structure of the cosmic web. So you do the math. 5%. That's us. That's everything you've ever seen or touched or tasted. Every star, every planet, every ocean, every person. 5% of the universe. The rest is dark, in both senses of the word, unseen and unknown. And yet, from that 5%, from that thin sliver of ordinary matter, the universe has managed to produce something astonishing. It's produced beings who can look back at the whole thing and ask how it happened. That's you. That's us. 5% of the universe, asking questions about the other 95%. There's something almost poetic about that. Now, I want to talk about something we haven't quite lingered on tonight, and it feels right to end with it. It's the question of what happens next, not to us, to the universe. Because the story doesn't stop here. The universe is still evolving. It's still expanding, still cooling, still changing. And if dark energy behaves the way we currently think it does, if it really is something like a cosmological constant, steady and unchanging, then the future of the universe is, well, it's a long, slow fade. Here's what happens. The expansion keeps accelerating. Galaxies that are far away from us are already receding faster than the speed of light. And that's fine. That's allowed by general relativity, because it's space itself that's expanding, not the galaxies moving through space. As the acceleration continues, more and more galaxies will cross that threshold. They'll slip beyond our observable horizon. Their light will never reach us again. From our perspective, they'll simply vanish. The observable universe will shrink, even as the actual universe grows. Our own galaxy, the Milky Way, will merge with Andromeda in about 4.5 billion years. That's already in motion. Andromeda is heading toward us right now at about 110 kilometers per second. The two galaxies will collide, their stars threading past each other like two swarms of bees passing through each other. And eventually, they'll settle into a single large elliptical galaxy that astronomers have already nicknamed Milkdromeda, which is a terrible name, but it's stuck. And that merged galaxy, along with a few smaller companions in our local group, will be essentially alone. Everything else will have receded beyond the horizon. The night sky, trillions of years from now, will be dark and empty except for the stars of our own merged galaxy. And those stars will eventually burn out. The sun will exhaust its hydrogen fuel in about 5 billion years, swell into a red giant, shed its outer layers, and leave behind a white dwarf, a dense, Earth-sized ember slowly cooling. Other stars will follow. The massive ones will go out first, in spectacular supernovae. The small red dwarfs, those dim, efficient little furnaces, will keep burning for trillions of years, far longer than the current age of the universe. But even they'll eventually run out of fuel, and when the last red dwarf flickers out, the universe will enter what cosmologists call the degenerate era. The only stellar remnants will be white dwarfs, neutron stars, and black holes, slowly cooling in an expanding void. And then, on timescales so vast, they make the current age of the universe look like the blink of an eye. We're talking 10 to the 37 years, 10 to the 40 years. Even protons might decay. If protons are unstable, and some grand unified theories suggest they might be, then eventually all ordinary matter will dissolve into a thin haze of electrons, positrons, neutrinos, and photons. The black holes will be the last structures standing, and even they won't last forever. Stephen Hawking showed in the 1970s that black holes radiate slowly, incredibly slowly, but they radiate. A stellar mass black hole would take something like 10 to the 67 years to evaporate. A supermassive black hole, the kind at the center of a galaxy, might take 10 to the 100 years. But eventually, even they'll be gone. And what's left is a universe at maximum entropy, a thin, cooling soup of particles and radiation spread across an incomprehensibly vast space, with nothing interesting ever happening again. Physicists call this the heat death of the universe. It's the ultimate equilibrium, the final silence. Now, that sounds bleak. I know. But here's the thing, and this is what I want to leave you with. That future is so unimaginably far away that it might as well be infinity. The universe is 13.8 billion years old. The last stars won't burn out for trillions of years. The last black holes won't evaporate for a number of years so large that writing it down would take more digits than there are atoms in the observable universe. We are in the very, very beginning of the story. Cosmically speaking, it's still the opening scene. The universe is young. Life is young. Consciousness is young. Everything interesting might still be ahead of us. And there's so much we don't know. Maybe dark energy isn't constant. Maybe it changes over time. Maybe the universe's fate isn't heat death at all. Maybe it's something we haven't imagined yet. Maybe the theory of quantum gravity, when someone finally cracks it, will reveal possibilities we can't currently conceive. The history of science is a history of surprises. Every century, something comes along that overturns what everyone thought was settled. There's no reason to think that won't keep happening. So here you are, lying in the dark, on a planet made of ancient stardust, in a universe that began as something smaller than an atom and has been expanding and cooling and complexifying for nearly 14 billion years. The hydrogen in the water in your body was made in the first 3 minutes after the Big Bang. The carbon in your bones, the oxygen in your lungs, the iron in your blood. All of it was forged in the cores of massive stars that lived and died before our sun was even born. You are, quite literally, the universe looking back at itself. You are the cosmos made conscious, lying in bed, breathing slowly, drifting towards sleep. And everything we talked about tonight, Lemaître's quiet insight, Hubble's red-shifted galaxies, Gamow and Alpher's nuclear calculations, Penzias and Wilson's accidental discovery of the cosmic microwave background, Guth's inflationary breakthrough, the COBE and WMAP, and Planck satellites painting the baby universe in exquisite detail, Zwicky's missing mass, Rubin's galaxy curves, the stunning discovery that the expansion of the universe is accelerating, the gravitational waves rippling through space-time from colliding black holes a billion light-years away. All of that is part of one continuous story. your story. The story of how everything got here, including you. And the most wonderful part, the part that I hope stays with you as you drift off, is that the story isn't finished. It's nowhere close to finished. There are questions out there right now about dark matter, about dark energy, about the very first instant of creation that someone is going to answer. Maybe not tomorrow, maybe not this decade, but the questions are real, and the tools are getting better, and the people working on them are brilliant and stubborn and endlessly curious, just like Lemaître was, just like Rubin was, just like every person in this story who looked up at the sky and refused to stop asking why. So let that thought settle over you like a blanket. The universe is vast and old, and mostly mysterious, and you are a small, warm, temporary arrangement of its atoms. And that is not a sad thing. That is an astonishing thing. You are here. You are aware. And for a little while tonight, you got to think about where it all came from. That's enough. That's more than enough. Let your eyes stay closed. Let your breathing slow. The universe will keep expanding while you sleep. The stars will keep burning. The galaxies will keep drifting apart. And somewhere, in a lab or an office or a quiet room not so different from yours, someone is staring at a whiteboard or a computer screen, working on the next piece of the puzzle. They'll still be at it in the morning. But for now, you can rest. You've come a long way tonight, all the way back to the beginning of everything. And now, it's time to let it all go.